So welcome to lecture 22 of MCS 507. So this is a review lecture for the midterm exam. So an exam about software. This is possible. We've done this before and we will do it again. So the purpose of this review lecture is to emphasize a little bit the most important topics. This review is based on the fall of 2019, and I'm also including the 2019 midterm questions here. So you can see that there is little surprise. So there is vectorization, symbolic computing, numeric computing, and then the connectivity. Visualization is often often the consequence of numerical computation. So first in this lecture I will say something about the way such an exam runs. I do not have the solutions to these review questions typed up. What I will try to do is with every question I will try to explain what I expect from a correct answer and what the purpose is of every question. Okay, so the exam is going to happen this coming Friday. And it can happen as an in-class conventional exam. That actually does not mean that you have to be in class. I will email you the exam questions and you will upload your answers, so everything can be happening from wherever you feel that it should best be happening. It's fine to come to class just as well. But the main point of what I call a conventional in-class exam is that it is very time limited, 50 minutes. Now you can choose both. The take-home exam is due on the Monday following, so you have a weekend essentially. I do not think that you should work the entire weekend on this. If you do that, then there might be something wrong with it. But so I would expect that within 4 hours you could do the exam. Either you do it on Monday morning or you do it in Friday afternoon. And actually the time that you have spent on the exam, it can actually then also be is not lost. So I will have the same type of questions for the in-class and for the take-home version. You can decide at the very last minute to take either version. Just do not upload your solution if you want to do the take-home version. Okay, first question, vectorization. So consider numerical integration, and this is the composite trapezoidal rule. As these formulas are there, then you see it's just a loop, and in Python, so this is here a question for Python, not for Julia. So in Python it would just be a couple of lines to define the approximation for this numerical integral. However, it would be extremely inefficient. Okay, now you can make a vectorized version. So that means that you assume that the function is vectorized itself. So that means that you can evaluate the function at an entire vector. So the question is then define the vectorization of this trapezoidal rule. How would you go about this? So this is a how-to question. it should be then clear. So the take-home version, so the in-class version can be a pen and paper and pencil version. Now, so we have been working with Jupyter notebooks. So you use the markdown cell to define things. Now, if it is working great, if it is correct Python code, great. But for the in-class version, it is sufficient to me that you show that you have an understanding of how things are or how they should be. Okay, in the take-home version, I actually expect that you have done both versions. So that means that you have done also the plain Python version with the loop, and that you have your vectorized version that works. But then also demonstrate that, say, for millions of function evaluations, and perhaps you may have to do this in a loop as well, that there is indeed a clear benefit of the vectorization. So that is the question explained. Now, how do you do this now? Well, in the formulas, you see that we start at the left bound at A, and then we compute the points where we're going to evaluate the functions. So the points A plus I times H. So in the vectorized version, you use a linspace command. NumPy has the command to define a range, an equidistant range of points in one single command. So this makes that the index computation, which would be done in Python is dynamically typed. It would have to do A plus I times H. It would each time have to figure out dynamically what the types are of these variables, and then it would need to compute and store things. With the vectorization, and it is the linspace, you will do everything in one single command, and most importantly, this is executed in compiled code. When you call the linspace, all the types of the arguments are assumed to be fixed. So you save the typing and you save the execution. Likewise, then we are going to evaluate a function such as the cosine function of NumPy that is vectorized at the entire linspace. Same benefit here. So you evaluate the entire function with prescribed types and by compiled code. And then the last step is to sum everything. And also that is better done by the built-in sum. So which you might already be doing if you are using list comprehensions from within Python. Okay, so that's the first question. So then we have symbolic computation and numerical computation. With symbolic computation, one can treat the formulas as you would write them on pen and paper. Here the purpose of the question is to do Lagrange interpolation, but then symbolically. So just as you see, so you define your Lagrange interpolation, your Lagrange polynomials, and you have a set of data points, data tuples, and you construct the interpolating Lagrange polynomial like that. So here again, it is important that you know how SymPy works a little bit. So you have to write Python code. If it works, this the better. But I should, in any solution, see that working with SymPy, working symbolically, is computing with symbols. So that means that you have to define a symbol for x. And from there on, you will compute everything with symbols. So for the previous question, it was important that you worked from within Python. Here, SymPy is also available in Julia, so it would also be not any different. Okay, so what is the purpose of the take-home question? The purpose of the take-home question is to define a module to work with Lagrange polynomials through the poly objects that SymPy provides. You can still work symbolically, so there is this property that the interpolation problem has a unique solution, and build that into a test. So certainly if you have exact integer coefficients and with integer data points, then the test can be computed exactly. Note that a problem in symbolic computation is that, and that's a problem in symbolic computation, deciding whether two expressions define the same thing. So here you may run into the normalization problem, as objects defined in the computer internally, they are of course different, but as mathematical objects they are the same. So you will have to normalize. So that means that you will have to reduce both your random polynomial and your interpolating polynomial through a normal form, which is by default the fully expanded version of the polynomial in the monomial basis. Okay, visualization, and again with polynomials here. So there is the theorem of Gauss-Lucas that states that the roots of a polynomial, the roots in the complex plane in general, they define a polygon. So the polygon that is defined is the convex hull of the tuples with the real and the imaginary parts. How would you go about to visualize this theorem? Using NumPy, SciPy, Matplotlib, or alternative also SageMath to illustrate the Gauss-Lucas theorem. You can also use Julia here in this question. So how long would it take you to actually take a random polynomial, compute the roots, take the convex hull of the polygon, and then plot the polygon? In the take-home question, and it's actually a design question, so if you can build your GUI, much better, but think about, and I would like to see some code, at least a layout, of a graphical user interface that would essentially draw the polygon on canvas. So you would, and probably I forgot to state the main point here of the theorem of Gauss-Lucas, and that is that the roots of the derivative are inside the convex hull of the polynomial spanned by the roots, of the roots. So your designed interface here would at least have a canvas element where you see the polygon, the roots, and then also the roots inside there. So when we were talking about graphical user interfaces, I used this bouncing billiard part problem, and mapping of coordinates inside the canvas was important there. Something similar will have to happen here. So when you think about a canvas, you think about pixel coordinates, when you think about roots of polynomials, well, these roots can be anywhere. So you have to calibrate when you compute. After you compute the roots, you will have to think about how to what is the minimum x value, the maximum x value. You have to scale things. So the advantage of matplotlib is that when you make a plot, the scaling is done automatically. So if you can do this yourself, if you're fully fledged graphical user interface, great. But at the solution, I would at least like to see that you are aware of this problem. That's the main difference between graphing, doing this on your own, or using Matplotlib. Okay, so then the fourth topic that we have discussed is how do programs communicate with each other. So here is a simple situation where we actually first introduced this with root finding. And I think I might have assigned this as a homework. I forgot. But suppose that you have two Python interpreters. You could think there is one old version with Python and then a newer version of Python that has not yet been extended with NumPy. So describe a mechanism for the Python interpreter that doesn't have the root finding capability to actually call the other Python interpreter. So we have seen a mechanism for that. The plain straightforward mechanism is to work through files and via the system call. There are better mechanisms, but they are more involved and more technical. So the first type of interfaces with calling other programs, it was then a precursor somehow to the web interfaces. So with web interfaces, you have also two programs that interacting with each other. You have the web browser and you have the server. The purpose of the take-home question is to design a form that accepts polynomials. So here this is a numerical root finder, although again in a very nice interface you would expect you could essentially accept anything that SymPy can do. Or you could see this as a prototype for a dedicated web service to compute roots of polynomial. Design the script. So with my server script, you can actually run it. So you can run it on localhost. So you need to write at least two scripts. One script that prints the form for the user to accept input, and then the other script would compute the roots and print the roots back. So we did a web determinant. This is kind of you could look into that lecture to see the answer to this. Okay, so this is the review in a nutshell. Let's go to the midterm exam of last time the course ran. So the first question is also a vectorization question. So consider this simple basic Monte Carlo method to estimate pi. And this is a great example for introducing list comprehensions as well. But describe how you would actually vectorize this. So you can do this. So list comprehensions are already an advantage. But with vectorization, you would use the random number generators that generate entire vectors. Um, we have seen the where command where we can do tests. So in the county, so the first part is instead of doing simple loops or making list comprehensions with all the points sitting in there, you call the random number generators of NumPy that will generate for you an entire vector of points right away. You apply the where command in the second step to do the tests. And then the third step is again the built-in summation on vectors. So the vectorization replaces these three steps by methods that work on vectors instead of individual Python instances of Python objects. The take-home version, you have to demonstrate essentially that the vectorized version of this program is a lot better than the straightforward definition of the method in Python. List comprehensions might be a little bit better, but there are still lists in Python. Vectors, the difference between vectors and lists, the main difference is actually that in a vector, all the elements are of the same type. That means that the accessing of the information is a lot faster. If you work with a Python list, the Python interpreter cannot assume that all the data elements are adjacent to each other. So it's a more complicated, a more flexible, but for computational purposes, less convenient way of working. Okay, then the symbolic computing version. Working with power series is a hybrid between symbolic exact computing. It's in some sense still computing with symbols, and in a way you still work exact, and also numerical approximate computation. So you are in essence computing with approximation. So we approximate, say, a cosine function by a truncated polynomial. So you can truncate after the second term. But the cosine being an even function means that you are already truncating after the quadratic term. Now, there is an important property is that power series, if the leading term is non-zero, then the power series is invertible. So demonstrate this with the cosine. Or another function, another power series. And do this with SymPy or Sage Math. Compute the inverse. Okay, so the take-home version is also here with power series. I think I probably truncated this a little bit. So in the PDF version, I have two sides. So one side is the Inclass version with everything that is here before the take-home question. And then on the back of the form, there is the take-home version, which would still contain the description of before. So the last three lines are in the context of power series. So you can define, if you can invert power series, you can actually define Newton's method. Newton's method, as you may know from numerical analysis on numbers or even from calculus, but it also works on power series that you can invert. So with symbolic computation, you can experience this. So you can compute power series that are roots of equations, where you compute the root. You compute an approximation for a function as a root of an equation. So if you think of the cosine again, how could you set this up? Well, you have the sine square plus cosine square equals 1. So given the expansion of the sine function, compute the expansion of the cosine function using Newton's method on that equation. And do this and verify that, or on any other example. So say verify with experiments. There might be simpler experiments. So the inversion, say of taking a square root, for example, could also be an interesting problem. Verify that Newton's method still converges quadratically. So the number of terms that you use in each iteration can actually double. So you can allow that the size of, so you have an input function that is in your equation. Initially you compute only a couple of terms, but then each time of that input function you also double the size of the input, and the size of the output would double correspondingly. Okay, roots, also numerically. When I introduced Julia, I introduced the eigenvalues of a randomly normal matrix. So here you would expect patterns of eigenvalues. And I did this experiment essentially with Julia, to advertising Julia and the linear algebra module, with the NumPy SciPy matplotlib. That's also a couple of statements. In the take-home questions, that would be the graphical user interface. So in the visualization, we have either always the built-in matplotlib or the plotting environment that you have from Julia, the plots packages. In the take-home versions, it's kind of interesting that you work with a canvas. Then, like with the other review problem, you have to deal a little bit with the rescaling of the eigenvalues. But that has the benefit that you could try to work in the reverse way. So that graphical user interface would allow you to kind of get a feeling about how the eigenvalues would modify. So you could add a scale to it and kind of try to look at the matrices that follow a certain pattern. So you can see the eigenvalue problem as a way to get plots of eigenvalues, but you could also start to construct matrices with prescribed eigenvalues. So via the diagonalization method, so that's the Schur theorem, you can try to get somehow a designing matrices with particular eigenvalues, but try to do this graphically. If your graphical user interface works, in that would be wonderful. But again, it would be good that you have at least a layout and that you kind of have thought about the critical methods that would need to be required here. Okay, so then the last question, so I will not even take up half an hour in this recording here, or a little bit more than half a recording. So it's a problem that was cloned off from the review. So instead of doing root finding, on the exam I did eigenvalue computations. And then also here the Inclass version would work with the file interaction mechanism, or you can be a little bit more fancier if you like and refer to pexpect. So that would be nicer mechanism, where we have two interpreters. I think there was a lecture where I introduced this as well. So either via the first mechanism that we did with mpsolve, you call the other program redirecting the input and then the output, or you use pexpect, which would allow you to, in case of Python, just to type in the same commands, but instead of executing them in interpreter A that can't do eigenvalue computations, they are being executed by interpreter B. And one can make that quite nicely working with pexpect. So one of the mechanisms is fine here. So the take-home question would be to um, have kind of a variation of what we did with the web determinant. So the web determinant printed table of text elements into a browser window, and through these text elements the user could enter all the coefficients of the matrix. So in the example in class we did compute the determinant, but here compute all the eigenvalues. So at the server side, and again you can practice this with the script myServer on localhost, so you need to define two scripts. The first script is actually already given via the web determinant that we have seen in class. The second script would then call the numpy eigenvalues. And in submitting your answer, it would be good that I could verify it rather quickly, provide some screenshots that you actually really have tested this, that it actually works. Okay, so I hope that this short review is useful. So I wish you good luck with the exam.